Hello, future engineers, subscribers, viewers, and students. Here is another video, part 2 of plane and solid geometry 4. And this video is devoted to problem solving. I hope that your skills, thinking skills, will be enhanced through these problems. Problem 3, two equal spheres intersect such that the surface of one sphere passes the centroid of the other sphere. If the radius of each sphere is 2 meters, find the volume common to both spheres. So this volume consists of two spherical segments of one base. So let's draw the figure. Since the radius of the sphere is 2 meters and each surface passes through the centroid of the other, so 2 meters is divided into 2, so 1 meter, 1 meter. And the volume of spherical segment is pi h square over 3 quantity 3r minus h. And r is 2 meters, h is 1 meter. And since there are two identical spherical segments, so the volume is doubled. So common volume is 2 times volume of spherical segment of one base. So it is equal to 2 times quantity pi times 1 square over 3 quantity 3 times 2 minus 1. 1 is the h, which is this. So computing volume, common volume is equal to 10.47 cubic meters. Problem 4. A 3-meter curved strip around and above the base of a hemispherical dome is to be covered with one coat of waterproofing compound which can spread at 120 square feet per gallon. How many gallons of the compound must be used if the diameter of the dome is 15 meters? So first, let's compute for the zone area. And let's have the figure. That's the figure. 1 gallon is 120 square feet. So we multiply 1 meter, which is 3.281 feet quantity square, so that we can express the spreading capacity of 1 gallon. And it is equal to 11.147 square meters. So 1 gallon can spread 11.147 square meters of area. So the number of gallons required is zone area times 1 gallon per 11.147 square meters. So from the figure, this is the curved strip of 3 meters and the radius of the dome is 7.5. So arc length S is equal to radius times central angle in radians. So 3 equals 7.5 times theta. So that means theta is 0.4 radians times 180 degrees over pi. Converting it to degrees, so theta is equal to 22.918 degrees. H therefore is equal to r sine of theta, 7.5 sine of 22.918. And height is equal to 2.9206 meters. From there, we can now compute the number of gallons. Zone area is 2 pi RH. This is the H. R is 7.5. So number of gallons is 2 pi times 7.5 times 2.9206 times quantity 1 gallon, which can spread 11.147 square meters. So the number of gallons required is equal to 12.35 gallons. Next problem. The ratio of the surface area of sphere A to the surface area of sphere B is 4. The ratio of the volume of sphere B to the volume of sphere C is 3. Find the ratio of the volume of sphere A to the volume of sphere C. So given area of A over area of B equals 4, and volume of B over volume of C, which is equal to 3. and we're looking for the ratio of volume of A to that of C. And in terms of surface area, it is equal to area of A to the 3 halves over area of C to the 3 halves. So first, we begin with the ratio volume of B over volume of C in terms of the surface area. So 3 volume of B equals volume of over volume of C equals 3 equals area of B to the 3 halves over area of C to the 3 halves. So that means area of B to the 3 halves is 3 times area sub C to the 3 halves. And since area of B is equal to 1/4 of the area of A, so we replace this by area of A over 4. So area of A over 4 raised to 3 halves equals 3 times area of C to the 3 halves. So that means we can now form the ratio area of A to the 3 halves over area of C to the 3 halves, which is this ratio of volume of A to volume of C. And it is equal to 4 to the 3 halves times 3. So since this area of A to the 3 halves over area of C to the 3 halves is also volume of A over volume of C, and we can now evaluate this value because this is 4 to the 3 halves is 8, square root of 4 is 2, 2 cubed is 8, 8 times 3 is 24. So therefore, volume of A over volume of C, which is equal to area of A to the 3 halves over area of C to the 3 halves, is equal to 24. So we proceed to problem 6. So we have a spherical segment has 2 parallel bases. The bigger base is a great circle with a radius of 80 centimeters. The smaller base has a radius of 30 cm, so it is a small circle. Find the area of the zone in square centimeters. So to help analyze the situation, let's draw the figure. So this is the great circle radius 80. So that's why this is also 80, and let's call this h. The radius of the small circle is 30. So that h is square root of 80 square minus 30 square. And the zone area is 2 pi RH, where r is the radius of the great circle, which is 80. So zone area is 2 pi RH, r is 80, and h is square root of 80 square minus 30 square. So substitute, zone area is 2 pi times 80 times square root of 80 square minus 30 square. So computing using your calculator there, the zone area is 37,278 square centimeters. Problem 7. A spherical steel ball having a radius of 10 centimeters is placed into a cylinder containing water at a depth of 20 cm. If the radius of the cylinder is 12 cm, by how high will the water level rise? So take note that the spherical steel ball will fit into the cylindrical container because the diameter is 20 and the diameter of the cylinder is 12 times 2, 24. So to help analyze the situation, this is now the figure. We have the sphere here of radius 10. It contains 20 centimeter deep. So it is the original level is supposedly level with the top surface, but because of the displaced volume by this sphere, then this displaced volume in the cylinder is also equal to volume of sphere. So that's the idea. Volume of sphere equals the change in volume in the cylinder. And volume of sphere 4/3 pi 10 cubed. Then volume of cylinder pi 12 square delta H. So solving for delta H using your calculator, cancel pi. Delta H is 2.959 centimeters. Problem 8. At 11 a.m., the water in a spherical tank was 1.8 meters deep. At 1 p.m., the water level dropped by 1.5 meters. How much water was used if the diameter of the tank is 4 meters? So let's have the figure first. This is the situation. So at 11 a.m., this was the level. The water is 1.8 meters deep, and it is below the center because the radius of the sphere is 2 meters. So therefore, this is 2 minus 1.8, so 0.2. Then at 1 p.m., the level dropped by 1.5, so this is the drop. And 1.8 minus 1.5 is 0.3, so that means this is 0.3. Therefore, 2 meters minus 0.3, so we have here a right triangle 1.7 meters high. For the first at 11 a.m., we have here a right triangle 2 meters radius of the sphere. This is 0.2. 2 meters minus 1.8 is 0.2, then call that A. Then at 1 p.m., this is 1.7, 2 minus 0.3 because this is 0.3, and that's 2 meters. I'll call this radius B. Then the volume used is the volume here, which is a spherical segment of 2 bases. And the volume of spherical segment with 2 bases is pi h over 6, quantity 3a squared plus 3b squared plus h squared. And this volume, formula for volume represented by this spherical segment with 2 bases is also the volume that is loose. So solving for a squared by Pythagoras theorem, by the way, h is 1.5 meters. A squared is 2 squared minus 0.2 squared. And that is equal to 3.96 square meters. B squared, on the other hand, is 2 squared minus 1.7 squared. And B squared is 1.11 square meters. Substitute into this formula, volume used is V pi times 1.5 over 6, quantity 3 times 3.96 plus 3 times 1.11 plus 1.5 squared. So using your calculator, the volume used is 13.71 cubic meters. Problem 9. A sphere is whittled down into a spherical sector with a central angle of 53 degrees and a volume of 420 cubic centimeters. What is the radius of the sphere? So formula for volume originally is 2/3 pi r squared times h, but because h is also equal to r minus r cosine theta over 2, so the volume is also volume of spherical sector is 2/3 pi r cubed quantity 1 minus cosine theta over 2. So 2/3 pi r cubed quantity 1 minus cosine theta over 2, where theta is 53 degrees. And volume is 420, so the unknown here is r. Substitute into the formula and solving for the radius. So 2/3 pi 420 is 2/3 pi r cubed quantity 1 minus cosine 53 degrees over 2. Solving for r is 12.40 centimeters. Problem 10. The base of a spherical pyramid is birectangular rectangle whose third angle is 23 degrees. Because it is birectangular, meaning to say the two angles are each 90 degrees. Therefore, the spherical axis is automatic this third angle 23 degrees. If the diameter of the sphere is 90 cm, radius is 45 cm, find the volume of the We call this spherical pyramid. So the volume in general is 1/3 Z sub S times R, where Z sub S is the area of the spherical triangle, which is pi R square E over 180 degrees. Recall from spherical trigonometry. So volume therefore is 1/3 pi R square E over 180 degrees times R. So it is equal to pi R cubed E over 540 degrees. So substituting everything, R is 45 and E spherical axis is 23 degrees. So the volume of the spherical pyramid is equal to 12,193 cubic centimeters. Problem 11. A donut has a circular section of radius 20 millimeters. Its centroid is 40 millimeters from the axis of rotation. Determine its volume in cubic centimeters and the total surface area, of course, in square centimeters. 20 mm is 2 cm and 40 mm is 4 cm. The volume by the second proposition of Pappus is area of the circle pi 2 squared, then distance traveled by the centroid is 2 pi times radius of revolution 4 cm. Without memorizing the formula. So volume equals area times distance, area of circle times distance. So it is equal to pi times 2 squared, then times quantity 2 pi times 4 cm. So volume is equal to 315.8 cubic centimeters, while the total surface area is circumference times distance traveled by the centroid, because the centroid of the circular region is also the centroid of the arc, circular arc, which is a circle, perfect circle. So whole circle. So this d is the same as 2 pi times 4. Circumference is 2 pi r, so 2 pi times 2, then quantity 2 pi times 4. So the surface area, total surface area is 315.8 square centimeters also. Problem 12. A closed container is in the shape of a paraboloid of devolution 1.8 meters across the top and 2.4 meters deep. Determine the volume when the water surface is 1.8 meters above the vortex. How deep will the water surface be when the tank is inverted? So volume of paraboloid of revolution is pi over 2 radius square, radius of the surface square, times depth or height 1.8. So let's draw the figure. This is the situation. The radius of the top of the tank is 0.9, half of 1.8. Then this is the depth, 2.4 meters, and this is the depth of water, 1.8 meters. So we need the radius of the water surface. I'll call that R. So this is volume of water, volume of air, and the radius is R. Then volume of water is pi over 2 r squared times height 1.8 or depth 1.8. Then to solve for r, we use squared property of parabola. R squared as to 1.8 equals 0.9 squared as to 2.4. So this is by squared property of parabola. R squared as to 1.8 equals 0.9 squared as to 2.4. So R squared is equal to 0.6075 square meters. Substitute here. So volume of water is equal to pi over 2 times quantity 0.6075 times 1.8. So the volume of water is 1.718 cubic meters. Therefore, the volume of air is volume of the tank, pi over 2 times 0.9 square times 2.4, then minus volume of water. So that's the inverted position. We're looking for D. And to solve for D, we need HA. But we need volume of air first. Volume of air is volume of the tank pi over 2.9 square times 2.4, then minus volume of water 1.718. So volume of air is equal to 1.3356, and we equate that to pi over 2 Ra squared. The radius of this part is denoted by Ra, times HA. Then to relate Ra and HA by squared property of parabola again, Ra squared as to HA equals 0.9 square as to 2.4. Ra square as to HA equals 0.9 square as to 2.4. So Ra square is equal to 0.9 square over 2.4, or 27 over 80 of HA. Substitute here. So 1.3356 equals pi over 2 times quantity 27 HA over 80 times HA. So from there, we can now solve for HA. HA is equal to 1.587 meters. So therefore, the depth is 2.4 minus HA. 2.4 minus 1.587. So the depth is, in the inverted position, the depth of water is 0.813 meter. Problem 13. A 60-degree elbow has a radius of 50 mm and its center line's radius of curvature is 120 mm. Find the volume and the surface area of the elbow. Let's express the answers in cubic centimeters and square centimeters respectively. So 50 mm is 5 centimeters, 120 mm is 12 centimeters. So volume by Pappus theorem is area of circle times distance traveled by the centroid. And since this is a 60-degree elbow, 60 degrees is pi over 3 radians, then the distance traveled by the centroid will just be radius of curvature 12 cm times central angle, which is pi over 3 radians. And the area is, of course, area of circle, pi times 5 squared. So volume is 5 times 5 squared times quantity 12 times pi over 3 radians. Pi over 3 is 60 degrees, and 12 is the radius of curvature. So solving for that volume of elbow, it is 987.0 cubic centimeters. For the area, it is equal to circumference times distance traveled by the centroid. The distance is the same, 12 times pi over 3. The circumference is 2 pi times radius of the circle, 2 pi times 5. So area is 2 pi times 5 times 12 times pi over 3. So using your calculator, the surface area is 394.8 square centimeters. Problem 14. If each side of a cube is increased by 1%, by what percent is the volume of the cube increased? So we can apply the principles on similar solids here. The new volume as to original volume equals the new dimension cube, which is 1.01 of the original E cube over original dimension E cube. So volume new as to volume original equals quantity 1.01 E cube over E cube, because the side of the cube is increased by 1%. So the new side would now be 1.01 of E. So cancel out E cube. The new volume is 1.0303 of the original volume. So that means this excess is the increase in the volume, and expressing it in percent, it is 3.03%. So percent increase in volume is 3.030%. Problem 15. An arch dam has the cross-section shown. Determine the mass of the dam if it is made up of masonry with a density of 2,200 kilograms per cubic meter. So mass is density times volume, and the volume is by Pappus second proposition, area of the cross-section of the dam, which is trapezoid, times distance traveled by the centroid of that trapezoid. And the distance traveled by the centroid of that trapezoid is simply distance from axis of rotation to that centroid times central angle 60 degrees, which is pi over 3 radians. So mass is density times volume, and volume is area of trapezoid times distance, and distance is, we will call the distance of the centroid of this trapezoid to the axis of rotation here as r. So it is r times 60 degrees or pi over 3 radians. So the area of the rectangle, let's divide this into two parts, the trapezoid into two parts, rectangle and triangle as shown. The area of the rectangle is 3 times 24. That's the centroid, and I will call that distance of centroid to axis of revolution as r. So to solve for r, we can solve that by Pappus, by Varignon's theorem rather. So the area of the rectangle is equal to 3 times 24, and it is 72 square meters. The area of the triangle is 1/2 of 3 times 24, and it is equal to 36 square meters. So therefore, the area of the trapezoid is area of rectangle plus area of triangle. 72 plus 36 is 108 square meters. Then we apply Varignon's theorem. 108 times r equals area of rectangle 72, distance of rectangle from axis of rotation is, this is 24 minus half of 3, 1.5, so 22.5. So 108 times r equals 72 times 22.5 plus 36 times 20. For the centroid of the triangle, this is 1/3 of 3, which is 1 plus 3, 4. So 18 plus 6, 24 minus 4 is 20. So that's why you have 20 here. So r therefore is equal to 65 over 3 meters. We then substitute into the formula. Mass is density 2,200 kilograms per cubic meter, and the area of trapezoid 108, and distance traveled by centroid is r times 60 degrees or r times pi over 3. So 2,200 times 108 times 65 over 3 times pi over 3, and that would be equal to 5,390,973 kilograms, or 5,391,000 kilograms if rounded off to 4 significant figures. Problem 16. Find the volume of an ellipsoid with semi-axis A9, B8, C7. What are the corresponding volumes of prolate and oblate spheroids? So for volume of ellipsoid, 4/3 pi ABC. So 4/3 pi times 9 times 8 times 7, and that is equal to 672 pi cubic units. For volume of prolate spheroid, remember the semi-ellipse is revolved about the major axis, that's prolate. So it is b that is squared. So it is 4/3 pi a b squared, because b equals c. So 4/3 pi 9 times 8 square, and volume of prolate spheroid is 768 pi cubic units. And volume of oblate spheroid, it is semi-ellipse revolve about the minor axis, so that in that case c is equal to a. So a is squared, volume is 4/3 pi a squared times b. Oblate spheroid, 4/3 pi 9 squared times 8. So volume of oblate spheroid is equal to 864 pi cubic units. Problem 17, a frustum of a cone has an upper base diameter of 2 meters and a lower base diameter of 6 meters. So big R is 3 and small r is 1. If the altitude is 5 meters, determine the lateral area of the frustum of a cone. Take note that the lateral area is equal to 1/2 quantity circumference of big base plus circumference of small base times slant height. The slant height is square root of big radius minus small radius square plus altitude square. And the lateral area can be reduced to pi quantity big R plus small r times slant height. Again, the slant height is square root of big R minus small r square plus altitude square. So it is square root of 29 meters. Substitute lateral area is pi quantity 3 plus 1 times square root of 29. So the lateral area is equal to 67.67 square meters. Problem 18. The altitude of a storage bin is 12 feet and the bases are parallel rectangles. The upper rectangle measures 11 feet by 14 feet while the lower rectangle measures 7 feet by 8 feet. So find the capacity of the bin. So this is not a frustum of a pyramid because the dimensions are not proportional. So instead, we compute the volume by the Prismoidal formula, and the midsection is the average of this dimension, 11 plus 7, 18 divided by 2, so 9 feet by 14 plus 18, 22 divided by 2, 11 feet. So the midsection is 9 by 11 feet. So formula for volume by Prismoidal formula, volume is L over 6 quantity area 1 plus 4 times area of midsection plus area 2. So area 1 is 11 times 14, area 2 7 by 8, area of midsection as mentioned earlier 9 by 11. So area of midsection is 9 times 11, where 9 is average of 11 and 7. 11 is the average of 14 and 8. So 99 square feet. Substitute into the formula where L is 12 feet. So volume equals 12 over 6, 11 by 14 plus 4 times 99 plus 7 times 8. So the volume is equal to 12 cubic feet. And finally, this is the last problem in this video. A globe is 24 centimeters in diameter, so 12 centimeters in radius. Determine the smaller area between meridians of 30 degrees east and 56 degrees east. Then B, between meridians of 20 degrees east and 35 degrees west. C, if a very small light bulb is positioned 20 centimeters from the center of the globe during nighttime, determine the area of the globe illuminated if there is no other light source. So let's focus first on A. So volume, this is a lune, and the angle between the meridians, between the dihedral planes is, because these are of the same longitude, so 56 minus 30 is 26 degrees. So area of lune as to 26 degrees equals area of sphere 4 pi r square 4 pi 12 square as to 360 degrees. So the area of the lune using your calculator is equal to 130.7 square centimeters. For the second part, this is 20 degrees east, 35 degrees west. So the angle between them, the smaller one, is 20 plus 35, so 55 degrees. So same formula, area of lune as to 55 degrees equals 4 pi times 12 square as to 360 degrees. So the area of the lune is equal to 276.5 square centimeters. Then in part C, The portion of the globe that is illuminated is the zone area. So to help analyze the situation, let's have the figure here. This is the bulb, and the distance of the bulb from the center of the globe is 20, as shown, 20 cm. And the radius of the globe is 12, and this is the light tangent to the surface of the globe. So it means that this radius and that light ray is 90 degrees. So we have similar triangles here. Actually, the upper right triangle is identical with the lower right triangle. We'll just consider the upper right triangle. If I call this theta, this is also theta. So areal illuminated is this portion here, which is zone, which is 2 pi rh. We need to solve for h. So if this is h, this part of this right triangle is radius 12 minus h. So by similar triangles, opposite as to hypotenuse, so 12 as to 20 for this big right triangle is equal to 12 minus h as to hypotenuse 12. So 12, zone area is 2 pi rh. We need to solve for h. R is 12. So 12 as to 20 equals 12 minus h as to 12. Solving for h is equal to 4.8 centimeters. So substitute here, the area illuminated is 2 pi times 12 times 4.8, and that is equal to 361.9 square centimeters. So that's it for this video.